Okay, so we're into week 3 for Geography 141, the natural environment. Again, this will be two separate lectures. The first lecture will talk about an overview of the reading that focuses on the atmosphere, and then the second lecture, or part 2, will focus on energy and radiation. So why do we even want to know about this stuff? Well, it's really critical that you have an understanding of the basic physics and the basic way that these systems work together, because the composition of the atmosphere is the buzz around global climate change. It impacts climate, it impacts weather, and in turn those elements impact erosion, the type of vegetation, wind speed, hurricanes, storms, all that kind of thing. So it's really important that you have a basic understanding of how atmospheric composition and structure is defined. The second part is to understand just this basic concept of energy, because it drives everything. So we have solar energy coming in. Well, it doesn't drive everything because, as I said before, we have that endogenic energy system, but the exogenic energy system really is the primary driver of climate, temperature, weather, and again erosion. And it's really important that you understand how that balance of incoming solar radiation and outgoing long-wave radiation work together. So the first part of the reading talks about different gases, talks about the gases of oxygen and nitrogen. I would like you to be able to kind of have a general idea that oxygen is 21% of the gases, nitrogen about 78% of the gases. And then why are they important? These are called constant gases, basically because the amount of nitrogen and oxygen have remained fairly constant through Earth's history as far as we can tell. And what is the function of nitrogen and oxygen? So you probably already know that nitrogen is critical for life on the planet. It's important as a component of protein, but we get that from meat, milk, eggs, plant tissues, and grain. So without nitrogen, we don't have the protein that we need. Oxygen is important for both plant and animal respiration, and in that whole carbon cycle of taking in carbon dioxide and releasing oxygen. So those are the main components of the constant gases, and then to have an understanding of the variable gases: carbon dioxide, methane, ozone, and then in general those atmospheric particles. Again, they're variable because those vary over time. They vary over time from in the history of the planet, and the carbon can vary from season to season. So look through that and just get a sense of what is the general composition, why are these gases important, being able to know that carbon dioxide is one of the major components of what are called the greenhouse gases, so is methane. There's a great video on ozone that I want you to watch and be able to talk about, what's causing the ozone hole, what do people think, or what do scientists think will be the result of climate change on the ozone layer. So it'll walk you through that. Here's a nice example of the variation of carbon. So you can see the black line indicates, or carbon dioxide, the black line indicates the average monthly carbon measurement from 2010 to 2015, and the red line is that just annual variation. And as you see, since 2010 to 2015, the amount of carbon in the air has indeed increased. The book also talks a lot about atmospheric particles, and these are really important aspects of our atmosphere, in that there are very small elements of dust, smoke, soot, and they have an impact on our sunsets. So they cause the refraction of solar radiation, the visible light spectrum. They cause those red molecules to actually refract, and that's why we see these lovely red sunsets or sunrises in the morning. And if you live in Oregon, if there's been a field burn, you notice that your sunsets are really spectacular. This can be natural causes, as in dust storms or natural fires or volcanic activity, eruptions, but it can also, and more often lately, is human causes, power plants, factories, that kind of stuff. So then the book brings you through kind of the atmospheric structure. And in the beginning of the chapter, they divide the overall atmosphere into two categories, the homosphere and the heterosphere. And the homosphere is that portion of the atmosphere that is closest to the surface of the Earth. And one of the things I want you to be able to do is to know the different layers and be able to discuss whether they increase with the temperature increases with temperature, or with altitude, or if the temperature stays the same or the temperature decreases with altitude. And this, in general, when we're especially in the troposphere, the higher in elevation you go, the cooler the temperatures, and this is called the environmental lapse rate of temperature, or how temperature generally changes with altitude. But one of the things that you see is when you get to the troposphere, even though you go higher in altitude, the temperature remains the same. And this is due in part to the ozone layer, which acts as a cap. So the tropopause kind of is capped off or held steady by the ozone layer, which is in the lower part of the stratosphere. Now, as you go up in altitude away from the planet in the stratosphere, you notice that the temperature actually decreases. And this is due to the ozone layer kind of absorbing that solar radiation from the sun. The stratopause, again, acts as a cap, and there's no change in temperature until you get to the mesosphere. And then again, as you go up in altitude in the mesosphere, the temperature again decreases. So I want you to be able to discuss that general relationship in the total atmosphere of the planet, and to understand particularly what's happening here in the troposphere. So here's a picture of a person hiking in I think it's July or August in the high Sierras. And so why is this guy having to wear a coat and hat? Well, you all would do this. Most of you would know this. And this is due to what we were looking at in the previous slide. So as you go up in altitude, there are fewer molecules of gas, and that those molecules of gas hold temperature. And so at the Earth's surface, the atmosphere actually has a weight, or it's 14.7 pounds per square inch of pressure on the Earth's surface. And the higher up you go, the less pressure there is, the less molecules there are, and therefore, in general, the lower temperature. One thing that you need to know to understand the incoming solar radiation and energy balance is that when we look at solar radiation, we're really focusing on the electromagnetic spectrum, which shows the range of energy that travels in waves from one source to the other. And we're looking at, or we're talking about, the energy from the sun that comes to the Earth in forms of visible light and ultraviolet light. And these are called shortwave radiation. They're more in the this area in the center where you see the rainbow pictures, and that's kind of the shorter wave. Long wave would be radio waves. And so we're looking at shortwave radiation coming from the sun. So how does that shortwave radiation, how is that connected to the greenhouse effect? So this is how most of you would be able to describe this without having taken this class. But so when solar radiation or insolation comes into the Earth, it comes in as shortwave radiation, which is as I said, visual light and ultraviolet light. And when that shortwave radiation hits the surface of the Earth, it is converted to long wave or heat radiation. And so you can have a glass surface like this greenhouse where the solar insolation or the shortwave radiation comes into the greenhouse, hits the floor of the greenhouse, and is converted into long wave radiation, and then is trapped in the greenhouse to heat up that building. So how does that work with greenhouse gases? So the same thing happens when you have cloud cover, is that carbon dioxide and methane are the primary contributors of greenhouse gases, and they're very good at holding long wave radiation. So if they're in the atmosphere, short wave radiation gets through the cloud cover or through the atmosphere to the planet, is converted to long wave radiation, and then gets trapped in the atmosphere, thus creating a really effective blanket. Now, there are natural causes for increased carbon dioxide and other gases in the air, and this is a great example looking at a volcanic explosion in the Philippines, which put huge plumes of atmospheric particles, carbon dioxide, sulfur into the atmosphere. The other cause is human introduced pollutants or atmospheric particles in the form of feedlots or factories. So not only do we have heat and increased absorption in the atmosphere from long wave radiation, we also can actually change the pH of rain. So one of the aspects of kind of this atmospheric pollutants is acid rain, and that can cause lots of issues on the planet. One is just erosion of elements like tombstones or building faces. They start to decay or erode. There's many areas that are called forest die-offs from too much acid in the rain, change the pH, and many dead lakes. So lots of people want to say that these fluctuations in carbon, temperature, etc. are natural. And so here is a graph from NASA website, the NASA climate website, that says yes, indeed, you can look at these fluctuations in carbon dioxide, and you can see that in the past, what was it, 600 and what did they say on here? 650,000 years before the present, you can see that atmospheric carbon dioxide has never been above this 300, I don't know if that's parts per million measurement. But since 1950 until today, you can see that almost vertical climb in carbon dioxide. So that's pretty much evidence that while there are natural fluctuations in carbon, human activity has contributed huge amount of increase in carbon. So that's kind of an overview. It's a lot of stuff. Take a look at this, do the reading, see if that will help you in answering your study guide.